Hello, this is Group 32 coming from the Pennsylvania State University, and we're here today to talk about our senior capstone project for ChemE 470. My name is Nana.
I'm Patra.
I'm Balkis.
And I'm Nazira.
And today we're going to be talking about our capstone project that is based on stem cell therapy for spinal cord injury. Now I'm just going to be talking in detail about some of our equipment. The first three, which are very important, is our wave bioreactors. The first one is a 2-liter bioreactor, second one is a 10-liter bioreactor, and the third is a 25-liter bioreactor. Now these wave bioreactors keep the cells in suspension and have a rocking wave type motion that basically helps in keeping the cells in suspension. For the first two are just the cells and the media. For the third bioreactor, we're gonna add the third 25-liter bioreactor. We're gonna add microcarriers to that bioreactor to provide a larger surface area for the larger expanded cells. So this is gonna be obtained from GE Healthcare. This is something that they developed for biotechnology, and it's a great equipment to use for this project. The second equipment I'm going to be talking about is our large NSC bioreactor, which is basically our main equipment. As I previously stated, it is a 400-liter bioreactor using perfusion-styled systems. We're going to be using microcarriers, and it has magnetic agitation. First, I will go ahead and say magnetic agitation because we're using magnetic agitation because the cells are very fragile and in nature, and using a typical traditional mechanical agitator will break up the cells and disrupt the process. And so we're going to be using magnetic agitation to keep the cells and microcarriers in suspension and to keep everything mixed properly. So the type of microcarriers we're going to be using is the Helix 2 type microcarriers, and they have a large surface area. They are positively charged, and because cells are negatively charged, we're going to be using utilizing the loss of attraction to help the cells adhere better to the microcarriers. The Helix 2 microcarriers are also not very porous, because using a very porous microcarrier makes separation difficult. Separation of the cell from the microcarrier is very difficult. And so in this bioreactor, basically everything has been specified. So one additional thing about this NSC reactor is that we're going to be using trypsin as a dissociation agent. So basically injecting trypsin into the system will help the cells to detach from the microcarriers and move on to the next process. This will be done in the separator, with the Harvestainer separator, which is basically the next step in the process. Balkis is going to come and take over and talk about the rest of the equipment descriptions.
The next is Harvestainer separator. Harvestainer separator will be used to separate the cells from microcarriers. Harvestainer separator is a single-use separator that contain 2 bags. It is a bag within a bag. The inner bag will trap all the microcarriers, and the second bag will collect all the media and the cells that is separated from the microcarriers. The cell will be pumped through the transfer port at the top of the separator and filter out at the bottom of the separator to be transferred to other bioreactors. This separator will have 0.7 separation efficiency. To help with the detachment of the cells from the microcarriers, trypsin is also added to the separator. Next, I will talk about the cryopreservation and vial filling. The cryopreservation is a process to help for the transportation and storage processes later. In this process, we will freeze the cells down until negative 130 degrees Celsius. To prevent the ice crystallization in the cells, the water content in the cells is substituted with DMSO and glycerol. After cryopreservation, the cell will be filled into the vial for easier transportation and storage. An aseptic vial filling will be used in this step. 5 ml of cryogenic vial tube will be filled up until 3 ml. In this vial, the cell will have a density of 1 million cells per milliliters. In doing all this, it must be in an airlock condition. The operating room will have a high clean room standard, and everything should be airlocked, and no access to outside should be open before the process is terminated. In designing the equipment design, we also consider the batch sizing and the production line. To calculate those numbers, we have considered the condition that is listed in the problem statement. Here is the three main conditions. The first condition is the target number of neural cells at the end of the bioreactors, which is 9 billion cells. There is also a number of doses per batch, which is 30 doses per batch. And in one dose, it should be 300 million cells per dose. Using all these conditions, we calculated the number of batch, which turns out to be 400 batch per year, to achieve 12,000 doses per year. And after calculating, in order to achieve this target, we need 7 lines of production. We also have a project timeline. Project timeline is when we estimate the number of time that the cells will spend time in each processes. The timeline is for making a batch of neural cells. It started with 4 hours in vial thawing, 84 hours in flask incubation, 100 hours in the first wave bioreactors, 100 hours in the second wave bioreactors, 41 hours in the third wave bioreactors, 10 hours in the separator, 151 hours in the big, large differentiation and expansion bioreactors, another 10 hours in the separation, and lastly 6 hours in vial preparation and filling. In between each of these processes, we also consider the time for cleaning the equipment and the time for transferring the cells from one equipment to another. After calculating all those time, we have came out the total time for one batch turns out to be 26 days and 21 hours. This is the process suite layout for the plant that we have designed. Each of the room in this plant will have a clean room standard, ISO standard, that is considered based on the processes that have been done in each room. Before anybody entering the plant, there will be an air shower and airlock condition where all the contamination from outside shouldn't be entered the building. In each room, we also have a safety measures in each room, like eye shower, eye wash, shower, and fire extinguisher.
In order to get the price for the productions for each batch, we have to take into account of the capital estimate cost. Capital estimate cost can be broken down into two types, which are IBL and OBL. IBL is the inside battery limit, which was calculated based on Aspen Process Economic Analyzers. For OBL, which is outside battery limit, it gives us the cost of the operations of the process and calculated based on batches of 1 year basis. On this slide, we can see capital estimate for this cell therapy projects. In IBL, we can see that the costs also include installations and also the cost of each equipment. For OBL, the only cost that we're concerned about is the process environmental cost. This is because the projects will be built onto an existing facility, so site developments, utilities, and raw materials and storage will not be included. For process environment, this is the cost of converting and improving the facility for it to be appropriate for our projects. The capital estimate is total to about $25 million. On this slide, it shows the economic analysis of the overall of these projects. As you can see, these include raw material costs, utility costs, disposable equipment costs, and also fixed costs. This project is a bit different from usual projects because this is a very new technologies. We could not find any price comparisons or price history of the products. So what we did was that we aimed for 15% rate of return, and we used Excel GoSeek to see what is the price per dose that we would have to pay in order to get 15%. And the results show that we have to pay about $7,800 per dose in order to get 15% rate of return. The overall total cash cost for this project per batch is about $220,000 per batch. As we see in the earlier slides, we can see that the cost of production for one dose is almost $8,000. We want to make sure that this kind of treatments is accessible to everyone, and so we wanted to lower the price of this production cost. We look into what can we lower, what are the most costs that makes the cash flow really high. So one of the things that was the main contribution to this high cost is the NSC media. Right now, the cost of NSC media is almost $600 per liter, and if we can get this down to about $300 or $350 per liter, it could save us a huge cost and also lower the price of production to about $5,000 instead. To do this graph, what I did was that I fixed the rate of return to 15% and then used GoSeek once again to find the cost at each price of NSC media. There are two ways that we could find an alternative, get a better price of NSC media. First is to find a cheaper alternative to NSC medias, or second, we could find a new technology that make this process more efficient.
So next I'll be discussing the outside battery limit and wrap up the rest of economic analysis for this project. The OBL for this particular project consists of 4 major components, which are the site development, utilities, the raw materials, and also the improvements that have to be done to build the facilities. As advised by our mentors, the site development for this project can be neglected as we are building these manufacturing facilities in existing facilities. So the first cost is the utilities cost. This cost is approximately $6,000 per batch and gives around $2 million per year. And the raw materials cost about $180,000 per batch, and which gives the $70 million per year. And finally, the cost for building improvements for the biopharmaceutical manufacturing facilities can be reached until $1.7 million. As we can see from these 4 major components, the most expensive would be the cost of raw materials. So to conclude the OBL for this project, we can see that the raw materials have the biggest sensitivities for the economic analysis. Other than price of the raw materials that can increase the production price for this project, we also have the other economic sensitivities, which is the plant capital cost. Right now we are at $25 million for the plant capital cost. So this number is very high to get the tax of return 15%. In order to reduce the production costs, we can reduce the production lines at around 3 production lines. As you can see from this graph, we are now at 7 production lines and we are at 25 million. We can reduce it to $13 million and get 15% of tax of return. In conclusion, based on the economic analysis and all the calculations that have been made throughout this project, the plan seems not profitable to proceed. This is because at the rate of return 15% and the price at $7,840 per dose, the present worth for this project is still in negative value. Because of that, the recommendation for this project is to reduce the production lines in order to reduce the production costs and also to get the present worth value positive. Other than that, we also can find other alternatives for the raw materials in order to reduce the operating costs and the overall cost for this project. That's all from us. Thank you.
We would like to thank all our project mentors and our instructor for all the help and guidance they provided for us throughout this semester and throughout this project.
ขอบคุณค่ะ
Edasi.
Terima kasih.